Good morning, everyone, and welcome to this lecture. This is lecture number 10 in electric current, and in this lecture, we will deal with what? With Kirchhoffs law. In the previous lecture, we had seen series parallel combination once again, and we had seen what happens in series and what happens in parallel. Just to have a quick recap. In series, current is same and voltage drop across various resistors are different. Everyone knows it. In parallel, voltage is same and the current across various elements are different. Everyone understands this? Yes or no? Okay. Yes or no? We understand this. We remember this.
Yes, sir.
Say na, sir. Okay. Then we had seen how we can find out power in different cases, how is power proportional, how we can find out voltage drop across two resistors. It is proportional to the resistance. We had solved some questions where we had found out the equivalent resistance between 2 points. Just to have a quick recap, series parallel combination we had seen. And I think this was the last question that we did, where a wire was bent in the form of a circle, and we had to find out the oops.
Yeah. Sir,
Yes,
can you explain the last question again?
what's wrong with the last question?
Sir, I didn't understand how did you get R1 and R2?
You did not understand how did I get R1 and R2. Okay. Did you understand the question that was before that?
Yes, sir.
How did I get R1 and R2 there? How did I get R1 and R2 there? Tell me. How did I get R1 and R2 in this question? The total resistance was 12 ohm. How did I get R1 and R2 in this question? Tell me. I got it in this question,
Sir,
right? How did I get it?
you divided the resistance into half on
Why?
the sides
Why?
because it's a circle.
So it's a circle, so what?
It's in 180 degree. It divides 180 degree.
That's it. Same logic you apply on this one. Same logic you apply on this one. Now it is not divided equally. One half is having 120 degrees and the other half is having 240 degrees. So how will the resistance divide? The half which is having 120 and the half which is having 240. If I call the 120 half as R1 or as R, the 220 half will be two times of that. Yes or no?
Yes, sir. But the thing is, how did you get R by 3 and 2R by 3?
Make the equation on your own. You call one resistance as R1, the second resistance becomes two times R1. Yes or no?
Yes, sir.
And R plus two times of R1, R1 plus two times of R1 should be equal to what? R1 plus two times R1 should be equal to what?
R.
Yes. Now find out the value of R1.
Understood, sir.
So it will come in that same ratio. R1 will come as R by 3 and R2 will come as 2R by 3. If you still don't understand, this is R1 and this blue one is R2. This R2 is 2 times of R1. R2 is 2 times of R1 and this is R1. Now if I add R1 with R2, I must get R1 plus 2 times of R1 should be equal to R. So R1 will be equal to R by 3. R2 would be equal to 2R by 3. And that is what we have applied here. Do we understand this?
Yes, sir. Thank you, sir.
Uh, Everyone understand this now?
Yes, sir.
Okay. Now, in today's class, we will move ahead and see Kirchhoff's law. So that is the next heading that we are going to write. Kirchhoff's law. Have you heard about this term Kirchhoff's law? Have you heard about this term Kirchhoff's law? Yes or no? No, yes.
Yes, sir.
Any idea what is this Kirchhoff's law? How many laws are there? Any idea? There are two Kirchhoff's law. Law number one is known as Kirchhoff's junction law. Some people also call it Kirchhoff's current law. You can also call it Kirchhoff's charge law. So, by any name you call it, it remains the same law. Anyone has any idea what is this law? Kirchhoff's current or junction or charge law. Yes?
Yes, sir.
What is that? This law is based on the law of conservation of charge. You can call it law of conservation of charge. You can call it law of conservation of charge, or you can call it law of conservation of current. What is this law of conservation of charge or called law of conservation of current? If you have this junction, this point A is a junction. When I say it's a junction, more than two current are meeting here. One current is coming from here, I1. One current is coming from here, I2. One current is going here, I3. One current is going here, I4. Now, whatever current is coming at junction A, the same current has to go out from junction A. Yes or no?
Yes, sir.
That is simply law of conservation of charge, or you can call it law of conservation of current. So from here you will get I1 plus I2, which is the incoming current, has to be equal to I3 plus I4. This small statement, this small statement is known as Kirchhoff's current law or Kirchhoff's junction law or Kirchhoff's charge law, because you can also write it in this way. You can also write it in this way. If A is a junction, Q1 charge is coming from here, Q2 charge is coming from here, Q3 charge is going out, Q4 charge. Q4 charge is going out. You can write whatever the charge is coming in. Q1 plus Q2 charge cannot be eaten up at the junction. Q1 plus Q3, Q1 plus Q2 has to be equal to Q3 plus Q4. You can also call this statement as Kirchhoff's current law or Kirchhoff's junction law or Kirchhoff's voltage law. Remember, this law is based on law of conservation of charge. And this is an important thing that you have to remember because I have seen many questions come on this, on which concept is this law based. So you must remember this. Everyone understands this? Yes or no?
Yes, sir.
Everyone knows this? Yes or no? Have you noted this down?
Yes, sir.
Pakka?
Yes, sir.
Okay, then I'll give you a question based on this. Everybody noted this down? This is a question from one of your previous years. I will put the entire question. This is the question. You have to find out the value of I. I, which is the current here. You have to find out the value of I. I'll give you 2 minutes to give me the answer for this one. It's a simple question from one of your previous years. Let me know once you get an answer. So the answer is option C, which is 23 ampere. How did you get 23 ampere? First of all, you have to understand what are the current in different branches. Yes. How did you get? It looks like a very complicated question.
No, sir. 5 amperes, 15 amperes, and 3 amperes are input current, and I is output current.
But
According
those
to
input currents are at different points. This 5 ampere is the input current at this point. This 15 ampere is the input current at this point. This 3 ampere current is the input at this point, and this I is the output from this point. They are at different points. How did you imagine that it would be 15 plus 3 plus 5? They were not inputs at the same points. They were inputs at different points. Yes or no?
yes, sir.
And how did you get it? Well, the answer is 23 ohms, and the answer is the logic is correct, but you have to understand that whatever current is coming in this entire thing cannot get lost. So whatever is coming in this entire bunch, instead of one junction, there are four junctions here. Doesn't matter. Whatever is coming in the entirety of this entire circuit, it cannot get lost. It has to go somewhere, right? Now, just to make you understand this, if I call this current as I1 and if I call things happen. Okay. So what I was saying was just to make you understand, if I call this current going in this branch as I1 and this current going in this branch as I2, I will be equal to I1 plus I2. Yes or no?
Yes, sir.
Now, if this current is I1, so this current will be 5 minus I1. Yes or no?
Yes, sir.
Okay. Now, if you go on and add and subtract the current in all the branches. Now, if you look at the blue branch, 5 minus I1 is coming from here and 15 is coming from here. So the outgoing current in this branch will be 15 plus 5 minus I1. Yes or no?
Yes, sir.
And then we have input current here and input current here. So this I2 will actually become 15 plus 5 plus 3 minus I1. So basically your I1 will go there and I1 plus I2 actually becomes equal to 23. So do we understand what I am saying here?
What?
So basically what happens is whatever current is coming, incoming current is coming, whether it's a junction or it is a series of junction, whatever current that moves out of that junction will be the sum. We understood this, yes or no?
Yes, sir.
Everyone understands this? So no matter how you do it, you will always end up with the same answer. The outgoing current is 23 ohm. Shall we move ahead on to the next thing?
Yes, sir.
Okay. The next thing is the second law. The second law is known as Kirchhoffs. Anyone? What is the name of the second law? Kirchhoffs loop law or Kirchhoffs voltage law. Kirchhoffs loop law or Kirchhoffs voltage law. Any idea what is this Kirchhoffs loop law or Kirchhoffs voltage law? Anyone? Anyone? No one has any idea? No one has any idea?
So the sum of all the resistance or potential is equals to 0 in a loop.
That is somewhat correct. Somewhat it is. You probably understand this, but you are not able to say this. Anyways, on what principle it is based on? So you must understand that this is based on law of conservation of what? This is based on law of conservation of energy. Electrostatic potential energy, I must add. So this law is based on the law of conservation of energy. Remember this because I have seen this question come in your NEET exam. On what principle is it based? So remember it is based on law of conservation of energy. So what it says, so I can write it in different ways. If you move in a closed loop, the change in electrostatic energy is zero. This is one way of writing it. Or the work done by electrostatic forces is zero. Or you can write it as change in potential is zero. The algebraic sum of changes in potential, the algebraic sum the algebraic sum of change in potential in a closed loop is zero. Now, if you have only battery and resistor in the circuit, you can write it like this: summation of E, the battery voltage, plus, oops, what I'm writing, plus summation of I into R. What is this I into R? What is this I into R? I into R is the potential drop across a resistor. I into R is the potential drop across a resistor. Do we understand this?
Yes, sir.
This is equal to zero. This is what this Kirchhoff's voltage law or Kirchhoff's loop law states, that if you move in a closed loop in a circuit, sorry, the change in potential is zero. I'll give you 2 minutes to note it down. Completed, then we will move ahead. Now remember, whenever you are going to apply this Kirchhoff's law, there is a sign convention that you have to follow. So the next heading is sign convention. Sign convention. The first sign convention is for battery. What is the sign convention for battery? What is the sign convention of battery? What is the sign convention of a battery? Anyone knows what is the sign convention of the battery? So, let us suppose that you are moving from point A to point B. So, I am moving like this from point A to point B across a battery. Now, current may flow in any direction, that doesn't matter. Current may flow in any direction, that doesn't matter. Now, here when I am moving in this direction, you can see this direction, the pink direction, yes or no? You are moving from positive terminal to negative terminal, yes or no?
Yes, sir.
That means you are moving from a point of higher potential to a point of lower potential, yes or no?
Yes, sir.
When you are moving from a point of higher potential to a point of lower potential, your potential will drop, yes or no?
Yes, sir.
And therefore it will be taken as negative. So this E will be taken as negative. Do we understand this?
Yes, sir.
E taken as negative, what does it mean? If I write my equation from point A to point B, and listen to me very carefully, listen to me very carefully, listen to me very carefully. If I write the equation from point A to point B, I may start from VA. What does VA stand for?
Potential at point A.
Okay, potential at point A. Now I go from the positive terminal to the negative terminal, so the potential drops. How much does it drop? Minus E. Do we understand this?
Yes, sir.
And then I reach point B. So this is how I can write my equation. VA minus E will be equal to VB, or I can say VA minus VB will be equal to E. Do we understand this?
Yes, sir.
Now let us do the next case. Here I am going from in this direction. As you can see, I am moving from negative to the positive terminal, no matter where the current is flowing. Current has got nothing to do with this. I am moving from negative terminal towards the positive terminal. Lower potential to higher potential. Do we understand this?
Yes, sir.
Therefore, your E will now be taken as positive. And I go from point B to point A in this fashion. Can you tell me how will the equation, if I write, look like?
VA plus E is equals to VB.
Take a deep breath. Look at what you, from where to where I'm moving, and then give me the answer.
VB plus E equals to VA. Sir, VB plus E is equals to VA.
Because I'm moving from B to A, VB plus E is equal to VA. Do we understand this?
Yes, sir.
So even if I write this equation, if I correct it, you can see VA minus VB is equal to E. This is the equation that I got in the first case, and this is the equation I am getting in the second case. Both the equations are same. That means I go from here to there or there to here, I will get the same result. Do we understand this, or this has gone above our head saying bye bye? So it doesn't matter how you go. You go from A to B or you go from B to A. The answer at the end will be same. Do we understand this, everyone? Can I have thumbs up from everyone in the class that we understand this? And this has not gone above our head saying bye bye. I'm not getting any response from the other class.
Understood, sir.
Understood, sir.
Have you noted it down, sir?
Yes, sir.
Yes, sir.
Shall we move ahead in life, sir?
Yes, sir.
The second sign convention comes for register or resistance. The second type of sign convention comes for register or resistance, and it is always similar. Remember, whenever you are moving from higher potential to lower potential, high to low, it will be negative. Do we understand this, or this has gone above our head saying bye bye? High to low is always negative. Shall we move ahead? Huh?
Yes, sir.
Now, look at this case. This is the case of a register or resistance. Now, look at how I'm moving. I am moving in this direction. I am moving in this direction. Do we see this? Pink is the direction in which you are writing the equation. We understand this.
Yes.
Okay. But now you have to look at the direction of current. The blue is the direction of current. So now you are moving in the direction of current. Do we understand this?
Yes, sir.
Current always flows from where to where? Higher to lower or lower to higher?
Higher to lower.
Therefore, in this case, the potential drop across this resistor will be taken as negative. Do we understand this?
Yes, sir.
Pakka, sir?
Yes, sir.
Now, if I write the equation, remember, I'm writing the equation from A to B. Can anyone help me in writing the equation from A to B?
Minus R is equals to V. VA.
Anyone can help me in writing the equation? No one knows it? Okay. So I start from point A, VA. I move in the direction of current minus I into R is equal to VB. I can write VA minus VB is equal to I into R. Do we understand this, or this has gone above what I'm saying? Bye bye.
Understood, sir.
Why were you not able to give me the answer, sir? What is the question, sir? Anyways, sir. Now we can take the case when we are moving opposite. As you can see, current is flowing in this direction. Now I'm moving opposite to the direction of current. When you are moving opposite to the direction of current, you are moving from a point of lower potential to higher potential. Yes or no?
Yes, sir.
So your potential should rise, and therefore it has to be taken as positive. Can anyone make the equation? Again, remember, we are moving in this direction. So equation has to start from which point?
Or point A, sir. Sir, point B.
నుండి ఇటు పోతుంది కదా.
Take a deep breath. Deep breath. Look at the direction. The green is the direction in which I am moving. Blue
Yes.
is the direction in which current is moving. It's not necessary that you move in the direction of current. We are moving in the green direction. Now tell me, from where will the equation start?
Sir, VB plus IR is equals to VA.
VB plus I into R is equal to VA. Now if you rearrange this, you again get the same result. So again you must understand, it does not matter from where to where you are making the equation, you will always end up with the same equation. Do we understand this? Yes or no?
Yes, sir.
Yes, sir.
Have you noted it down, sir?
Yes, sir.
Everyone, sir?
Yes, sir.
Yes, sir.
The next element is our favorite capacitor. Capacitor. Do you remember capacitor, or we have forgotten capacitor?
We remember, sir.
Thank God, sir, that you remember. Students have this habit of forgetting things.
Book it.
Again, capacitor.
Sir, Q is equals to CV.
Q is equal to CV. That is the only formula we have read. Okay. Again, we do the same thing. Now the capacitor is just like a battery because it has a positive terminal and a negative terminal. Do we understand this?
Yes, sir.
Now if I move like this in this direction, you can see we are moving from which terminal to which terminal?
Negative to positive.
So the potential drop, we are moving from lower potential to higher potential. So the drop will be taken as positive. Yes or no? No or yes?
Yes, sir.
Again, I come to the same scenario. Can you write the equation, sir?
Trend is lower to higher.
Lower to higher when it is taking like a direction.
Yeah, see. So negative.
No one can write the equation, sir?
See,
Okay. VA potential rises. So plus Q by C is equal to, remember Q is equal to CV. That is the only equation we have seen. So V is equal to Q by C.
Also, it's same.
no.
So from here I can get VB minus VA is equal to Q by C. Do we understand this? Or this has gone above our head saying bye bye?
Understood, sir.
Pakka, sir? Everyone, sir? Huh?
Yes, sir.
In the second case, I may move from B to A, green direction. Then I move from positive terminal to negative terminal. I move from higher potential to lower potential.
Yeah.
Can anyone write the equation from B to A?
By C.
VB minus Q by C is equals to VA.
VB minus Q by C is equal to VA, or I can write VB minus VA is equal to Q by C. Do we understand this?
Yes, sir.
Now, as you can see, it doesn't matter from where to where you move. It doesn't matter. The answer still remains same. Yes or no?
Yes, sir.
Okay. One last element remains. Everyone has noted this down. Yes or no? No, yes. Huh?
Yes, sir.
Other class, are we there in the same dimension, or we have taken some interdimensional portal and teleported ourselves to another universe? Are we there? Same universe. F is equal to MA. Valid, no?
Yes, sir.
Okay. Thank God. This generation has got the capabilities of moving into higher dimensions without even knowing. They have so much of energy they can instantly teleport themselves from one dimension to the other dimension. So I must check whether they are still in the same dimension. The last element which we are not going to study now, but we are going to study in the future. So I can also see future. In the future is known as, anyone knows the name? The first one was resistor. The second was second was capacitor. What is the third one? Inductor. All are terms. Inductor. All the devices that you see around you are a combination of these three gentlemen. It could be a resistor or a capacitor or an inductor or combination. Anyways, since we have come to this stage, we must also do this, and we can also do questions, and we can wind this Kirchhoffs law once and for all. Again, we have a sign convention for this gentleman. Again, same thing. But here we don't know the potential drop. It is L into di by dt, where di by dt is the change in current, rate of change of current. For capacitor, it is Q by C. For resistor, is potential drop is I into R. For inductor, it is L di by dt. L is the inductance of the inductor. We have not read this term, but don't worry. L, the inductance will be given. Di by dt is the change of current, rate of change of current, that will also be given. We are not going to solve question on this. We'll only solve question on this in the chapter when it comes. Right now, just see the sign convention because we are in the mood, so we should finish it. Again, I move in the direction like this from A to B. My fellow current is also moving in the same direction. So I'm moving from a point of higher potential to lower potential. So so this will be a drop. Do we understand this, or this has gone above and saying bye bye?
Understood, sir.
Thank God, sir. You understand that, sir? So it will be taken as negative. I will write the equation for this because you might get confused. Nothing to get confused here actually. VA minus L di by dt is equal to VB. VA minus VB is L di by dt. We'll only do questions of this when we actually come to that topic. Just now write it because we are writing the sign convention of everyone. This inductor will feel left out. So let not it feel let out. In old movies, there used to be a stepson, Sotela Beta. So the Sotela Beta or Beti always, the stepson always used to have partial treatment. The mother never used to love that Sotela Beta. So let's not make this the Sotela Beta. So let it give the attention it deserves. So that's why I have done it. So that it does not look like a Sotela Beta. Stepson. If I move, wrong color. I hate wrong colors. If I move from here to here, I move opposite to the direction of current. Do we understand this? Yes or no? Huh? Do we understand this?
Yes,
Are we
sir.
there? Same dimension, no?
Yes,
Sir.
Equal to MA. So if I move from there, VB plus LDI by dt is equal to VA. You look from here, you look from there, you come from here, you come from there. The concept remains the same, and this remains the answer. Everyone understands this? Yes or no?
yes, sir.
Now this has gone above our thing. Bye bye. Oops. Everyone understands this?
Yes, sir.
Okay, now, sir.
Akka, sir.
Have you noted this down?
Yes, sir.
Okay, sir.
Yes, sir.
Okay, sir. Can I give you a question, sir?
Yes, sir.
This is point A, my dear friend. This is point B. The current flowing is 2 ampere. This is 2 volt. This is 5 volt. This is 3 ohm. This is 6 ohm. Anyone understand? This is a part of a circuit that I have brought for you and put it in front of your eyes, for your eyes only. It was a James Bond movie, for your eyes only. Way before I was even born. For your eyes only, and you have to find out VA minus VB. How much is VA minus VB? And I shall give you 2 minutes to give me the answer. You can do this, yes or no? Ah,
Yes, sir.
2 minutes. Okay.
Sir, wait.
So I will move like this in this direction from A to B. Let us make the equations together. Let us start from the point A, VA. Now what? We are moving across this battery. From where to where are we moving? From the positive to the negative terminal. Yes or no?
Yes, sir.
So will it be positive or will it be negative?
Negative.
So VA minus 2 volt. Let's write it as 2. Then I am moving across the register and I am moving in the direction. So will it be positive or negative? For the register, will it be positive or negative?
Negative, sir.
How much negative?
-3.
Take a deep breath and then give me
Sir,
the answer.
-6.
Yes, you have to take a deep breath always. Always take a deep breath. Good. Then I see this this battery and I move from negative to the positive. So what happens? Tell me fast.
Positive.
Plus how much positive?
Yeah.
Not 5 into 2, huh? It's only 5. Do we understand this?
Yes, sir.
Then I move across the last gentleman.
Positive to negative.
Sir, 12 plus
Plus or minus?
plus 12. How 30?
Deep breath. Deep breath. Take a deep breath and give me the answer. Look at the direction of current.
Negative. Is it positive?
No.
So it is minus 12. 6 into 2 is equal to VB. From here, you can calculate the value of VA minus VB. Do you understand this? Yes or no?
Yes, sir.
Okay, we'll continue and we'll continue with Kirchhoffs law in the next class, and hopefully by the next class we will be able to make equations more confidently and without mistake. Do we understand this? Yes or no?
Yes, sir.
Anyone understands this?
Yes, sir.
Okay, then we'll continue our discussion in the next class. Take care. Goodbye. I'll see you in the next class. Bye bye.
Bye, sir.